as I was saying, we've covered reactivity, and now this stuff is an application of that. All right? Two types of electrochemical cells. One that converts chemical energy, stored chemical potential energy, into electrical. That's these voltaic ones that we're going to look at in section 2.4. And then the other one converts electrical energy into stored chemical energy. So the exact opposite, and that's called an electrolytic cell. And each cell has its own use. So let's start by looking at these voltaic ones. You may not know, you probably don't know, that you come into contact with these all the time. In fact, right now, everybody here has a voltaic cell on their person. Everyone has one on their person. Because I'm pretty sure everybody in here has a cell phone, and that little battery in the cell phone is a voltaic cell. It's what we use as a battery. We call it a battery. Okay? They convert chemical energy into electrical energy, and they do that by allowing a spontaneous reaction. Oh, there's that term again. A spontaneous reaction to happen. Now, if we take something like those reactions we were looking at in the formative quiz we just did, and we say put iron with, what do we have it with? I think silver or something like that. If I take a stick of iron or a strip of iron and I throw it into a silver solution, it's going to react spontaneously. The silver ions are going to gain electrons from the iron atoms. The iron atoms are going to turn into ions, and the silver ions are going to turn into solid silver atoms. All right? Now, we've been seeing that since grade 10. That's a single replacement reaction. All we're saying with this is we're going to let that same reaction happen, but we're not going to physically allow the iron to touch the silver solution. Instead, what we're going to do is we're going to have the iron in its own solution, and it's going to be physically separated from the silver solution, and the only connection that we're going to have between the iron strip and the silver solution is a piece of wire that connects the iron to a strip of silver that's sitting in the solution. And so if the electrons are going to transfer, and they will, we already know that, they have to go out through the wire and then into the solution, and then they can be gained by silver in the solution, and it'll form silver solid on that electrode that's in the silver solution. Usually it's a silver electrode. But if we put a device, like your cell phone, any other device, light bulb, voltmeter, in series, so in that circuit with that wire, that flow of electrons will operate that device. And that's what a battery is. That's really what we're doing with a voltaic cell. Okay? So, as I said, we commonly call these batteries, but in actual fact, a battery is not a single voltaic cell, but it's multiple voltaic cells that are wired together in a circuit, in a series circuit. Okay? So, for example, if you have one of these graphing calculators, one of these is just a cell, just a voltaic cell. But if I take the entire bank of these as one thing, that entire bank of 1, 2, 3, 4 Duracell cells is one battery. So this entire thing is considered a battery, truly, and one individual one is just considered a voltaic cell. Does that make sense? Now, we don't often think of, your graphing calculator and the 4 batteries that are in the back as a battery. But one that we do often think of as a battery, and we call it a battery rightfully, and it's truly a battery, is those little 9-volt batteries. You know the 9-volt that's like a box and it's got the 2 little things on the top, you snap the thing on? That's a true battery. If you were to cut away the casing, you would see that what you have is 6 1.5 volt cells that are connected together in series, and when you get 6 1.5 volt cells, you get 9 volts in total. And so that's how you get your 9-volt battery. Okay? All right, so voltaic cell is simply a spontaneous reaction in which we decide the path the electrons will take in the transfer process. So we force the electrons to go through the path that we want through an external circuit, which is a wire. For example, the wiring or circuitry in your calculator or your cell phone. And then they're going to be gained, just like they always have, by an oxidizing agent at another electrode called the cathode. All voltaic cells are built on the same basic format. A reduction reaction occurs in one container or one compartment of the cell. That's called a half cell. And an oxidation reaction occurs in another container or another compartment called a half cell. And they're physically separated by a barrier, okay? But it's got to be a porous barrier. It allows ion movement, but doesn't actually allow the solutions to mix, okay? So the two half cells are, as I said, connected by a porous barrier internally and by a conducting wire externally. So there are two connections, an internal connection between the solutions and an external connection between the electrodes, okay? The barrier separates the half cells, but allows ions to move back and forth, okay? And the wire allows electrons to move between the two half cells. So some terminology here. In each container there's a solid electrical conductor that's called an electrode. Sometimes it's made out of the metal that the ions, or the solid metal that the ions are in the solution. I know that sounds awkward, but so for example, if I have a zinc solution, I'll make the electrode out of solid zinc. If I have a silver solution, I make the electrode out of solid silver. Sometimes that's not possible. If I wanted to react hydrogen ions, for example, in an acid in solution, well, obviously I can't make an electrode out of solid hydrogen, so I'd use an inert electrode, something like carbon or platinum, and I'd put that in, and so the ions, the hydrogen ions, could act as my oxidizing agent, gain electrons and form hydrogen gas, but the electrode that's conducting the electrons into the solution, just leaving them in there, would be something like a carbon rod, okay? And that way, it's not going to react itself, but it's a good conductor. It just brings the electrons in. When the two half cells are connected by the wire, electrons leave the oxidation half cell called the anode, okay? They move through the wire to the reduction half cell that's called the cathode. That's called the external circuit, through the wire and to the cathode. And if we connect a device, like say for example a calculator, into that external circuit, that flow of electrons will operate the device. This diagram here came straight out of your textbook, page 89, and it's your typical voltaic cell diagram. Oh, the labels will be different depending on, you know, what you're using as far as your electrodes and your electrolytes. Usually, like a standard set of labels on this is to label the electrode in each case, to label the electrolyte in each case, to label the salt bridge in each case. Okay, so that it's all fully labeled, but the diagram itself for a voltaic cell is always going to look like this: two separate beakers. This salt bridge here is simply a glass tube that's filled with a solution, an electrolytic solution. Usually, what I use for a salt bridge is sodium nitrate, NaNO3. It's a safe salt bridge. It works for every single cell. So that's my go-to salt bridge. That's what I use. You'll always have the electrodes, the external wire that I was talking about, and then usually a voltmeter in series, so that you can take the voltage that you're producing. So why do we need this salt bridge? I mean, it's fairly obvious. You're going to need the zinc electrode because the zinc atoms are going to lose electrons. That's your source of electrons. And you need the copper ions in the copper solution, the other side, to gain those electrons. And so it stands to reason you're going to need something like a solid copper electrode to let those atoms stick to. Well, why do we need a salt bridge? What's the salt bridge for? That's the big question that everybody always asks. But if you think about what's happening, it kind of makes sense. As the zinc loses electrons, it forms zinc ions, 2+ ions, that go into solution at this side, at the zinc side of things. Now understand that before we let it run, the solution is neutral, electrically neutral. And that means that you got the same number of zincs ions or positives as you have, say, nitrate ions, negatives. And so with an equal number of positives and negatives, it's electrically neutral. There's no charge on that solution. And the same thing happens at the other side over here with the copper, that you have an equal number of positive ions as negative ions, and so that solution is neutral to start with. But as soon as I flip the switch and I allow oxidation and reduction to start occurring, let's take a look at what really happens to the charge in these solutions. As the zinc at this side is oxidized, it forms zinc ions that go into solution. The zinc ions are positive, aren't they? So although I may start off with equal number of positives and negatives, it won't take very long, only a couple of atoms, to lose electrons before I have more zinc ions and I have nitrates, and this solution at this side becomes positive because now I got more pluses than negatives in there. At the same time, as a couple of these, the first couple ions of copper gain electrons and form neutral copper on that electrode, I now have more negatives than positives over here. You see what happens? The solutions themselves become charged. And here's what the salt bridge does for us. When the negative electrons, they have to, when they leave the anode side, and they have to migrate through the wire to the cathode side. That's the way this all works. But they're not going to leave the anode if the anode's positive, is it? Because if that solution's positive, it's going to attract electrons, it's not going to let them leave. And it's certainly not going to migrate towards a solution that's negative at the cathode. It's going to be repelled. And that's where the salt bridge comes in. You see, this salt bridge contains an electrolytic solution, a solution that contains positive and negative ions. That's why I use sodium nitrate, very, very soluble. And so the ions in the salt bridge are able to migrate one way or the other so that it neutralizes any charge that's building up. So, as positive ions come out of solution at the cathode because they're gaining electrons and forming a solid, positive ions in the salt bridge move into this solution and it keeps everything electrically neutral, no charge. As the zinc in this case forms zinc ions and this solution starts to become positive, negative ions from the salt bridge move into this solution and keep everything neutral. Again, making sure everything is electrically zero charge. As long as there's a zero charge in the solutions, electrons will continue to flow in that external circuit. So the electrons will continue to go from here across and down. We don't want those solutions to become charged, and that's what the salt bridge does. And for that matter, as positive ions come out of the salt bridge here, some of these zinc ions that are positive will go into the salt bridge this way. And as negative ions come out of the salt bridge over here, negative ions from this side will move into the salt bridge to replace it so that everything stays electrically neutral. That salt bridge is a path for positive and negative ions to flow back and forth in solution to keep the solutions from becoming charged. Okay? So that's kind of all I've outlined at the bottom here, that the solution in the half cell becomes positively charged, and as the cathode gains electrons, the solution becomes negatively charged. At that side, these charged solutions cause the electron flow to stop. Salt bridge allows positive cations to migrate to the cathode. So That's one of the labels we always put on these diagrams is what is your anion and cation migration. Cations always migrate through the salt bridge to the cathode, and anions always migrate through the salt bridge to the anode. So an to an and cat to cat. So if we take a look real quickly at one of these, well, if I just look at the entire thing here and close the switch off, watch what's happening here. First, we get electrons flowing down here, and look what happens. Two of those ions that are silver gained electrons, formed solid silver. And while that happened, one of these atoms over on this side lost electrons, forming a 2+ ion, and the electrons went up and across. Another 2 electrons come down, another 2 electrons go up. Okay? Let's take a look at what's happening individually in every section of this, though. So let's first take a look at the cathode half reaction. So this is the cathode, the silver side of things. And so we can see we got 1, 2, 3, 4, 5, 6, 7, 8. And now we got 1, 2, 3, 4, 5, 6 positives. Well, if we had 8 positives and 8 negatives, we now have more negatives than positives, don't we? And if 2 more come out, now we even got more negatives than positives, because without the salt bridge, the number of negatives hasn't changed. Okay? If we take a look at the anode side of things, here we've got 2, 4, 6. And now we've got 2, 4, 6, 8. So notice what's happened with this guy. As one positive ion came in, this positive ion left through the salt bridge. If the salt bridge wasn't there, we'd have too many positives, wouldn't we? And so as one ion comes in, one ion goes out through the salt bridge. Okay? And so if we look at what's really going on in that salt bridge, and we focus, look at what's happening here. We have electrons that just left, so we made a positive 2+, and this positive 2+ came in here. We gained electrons and took ions out of solution, and look, we've got ions, positive ions from the salt bridge that are now migrating into this side. At the same time, look what's happened to this negative. The negative's going out because it wants to maintain that charge balance. So we got positives moving in, negatives going out, maintains that charge balance. We have positives leaving and negatives coming in here, so that again we maintain the charge balance in the solution. As long as the charges are balanced, everything keeps on flowing. The charges become unbalanced, the charges stop, the electrons stop flowing. That make sense? That's why we need the salt bridge. So, a little bit of a summary on voltaic cells. Oxidation reaction always occurs at the anode. Always occurs at the anode. The reduction reaction always occurs at the cathode. Reductions at the cathode, oxidations at the anode. The charge assigned to the electrode. So, in a battery you have a negative terminal and a positive terminal. The charge on the anode, that's our negative electrode. The reason we assign it that way is because it's the source of electrons. Or you can think of it as it's where in the internal circuit, it's where the anions, the negative ions, migrate to is the anode. Okay? The cathode is considered the positive electrode. And again, it's because it's the destination for electrons, or you can think of it in terms of it's where the cations in solution migrate towards. the ones I've got highlighted here are pretty important. That's why they're highlighted. Electron flow is always the anode to the cathode. Now, I always used to remember it when I was a student. It goes down the alphabet, A to C. Okay? Electron flow is always in the external circuit. It's not something I've got written in here, but you may want to jot that in. It's always in the external circuit, okay, through the wire. Positive ion flow, that's cation flow, is always towards the cathode, and that's through the salt bridge. So cations to cathode, cat to cat. Anion flow, or negative ion flow, is always towards the anode, again through the salt bridge. An to an, cat to cat. Okay, any questions with that? Well, that's voltaic cells. In Chem, we have a chemist shorthand when we're representing these cells. Okay, and every part of the little shorthand notation means something. It's called cell notation. And again, I cut and pasted this right off of page 91 in your text. So here's what it looks like. In cell notation, the left-hand side of this double bar, double vertical line, is always your anode side. We start with the electrode that the anode is made out of. Then we have a single line, which represents a physical contact barrier, a physical interface between the electrode and the solution. And we list in the solution the relevant ions. So in this case, it's the zinc 2+ that's in solution. So what this is saying is I have a solid zinc anode in a zinc solution. The double vertical line represents my salt bridge. And then on the other side of that is all of my cathode stuff. So this is my reduction stuff. And so the solution at the cathode side is the copper ion. And then it's in physical contact with a piece of solid copper as the electrode, the cathode. Okay? That's how we read this short form. Well, the last little bit they talk about in section 2.4 is that the diagrams we looked at, the little video or the little thing that we used to kind of learn about this works great for demonstration purposes, but if you take your battery out of your calculator and you shake it, it's not going to joggle, or it's not going to slosh. There's no liquids in there. Okay, so that's what we've said. Typical battery uses a voltaic cell as illustrated on page 93 in the text. Voltaic cells using beakers and solutions is great for learning how they all work, but it's not practical for everyday use. So instead, we use something like this. And here's your this is a double A, same idea with the triple A. If we cut it away, here's essentially what we've got. The electrolytes, the solutions aren't solutions, they're a paste. Okay? So we thicken them, and realistically, the very first cells like this, the very first voltaic cells that were usable like this were called Leclanché cells. They invented or they were developed by a French scientist named Leclanché. And all he did was took the solutions and thickened them with cornstarch. So you know how you'd make gravy at Christmas time and you thicken the drippings with cornstarch? Did the same thing. Put cornstarch into the solution and thickened it with cornstarch and made it into a paste. And that's pretty much the same type of thing we do today. Granted, we're using, if you look in here, we're using a little bit different compounds, a little bit different materials, so that we can use less of it. It lasts longer, produces a better voltage, but the basic design is the same. We have an electrolytic paste that contains this oxidizing agent, the manganese dioxide, ammonium chloride, as a mixture in this paste. We have a paper barrier, that's this right here, and that barrier is separating the zinc electrode. And the zinc, in the case of our batteries, is the actual casing in the battery. The metal casing is made out of zinc. So that's your actual anode. And this paper barrier separates the oxidizing agent, which is the paste, from the reducing agent, which is your zinc casing. You have a bit of an airspace here, just in case gases form or something. You've got airspace that can take up that gas, okay, and it's compressible. Down the middle, connected to that little dimple at the top of your battery, is a carbon rod, and it's making physical contact with your paste. And then we have some insulators, and on the very top, that's what makes up that dimple, is a steel cap. And that steel cap is connected to your carbon rod, but notice that the insulator is keeping it from being connected to the zinc. And so the zinc casing at the bottom here, notice it's connected to a metal cap at the bottom that's your negative terminal. So when we connect this to something like a light bulb, the electrons will go from the zinc, conducting through this metal case. It'll go out through the circuit, run your little light bulb, like let's say it's a flashlight. It'll come back in through this top metal case, down the carbon rod, and will be gained by the oxidizing agents in the paste here. And so these oxidizing agents are gaining electrons, causing electrons to leave the zinc casing, go all the way around, and be gained. The reason that your battery doesn't burst open, or shouldn't burst open, is that you have less ions in the paste than are required to react all of the zinc. So the zinc maintains its thickness and its integrity. Okay? If that doesn't happen, the zinc casing will rupture, and you get battery stuff leaking all over the place. Because oftentimes these have the electrolyte is not just the two things you're seeing here, but there's also some base in there. So they're alkaline, and so you get base leaking out, and that's never good. It destroys a lot of stuff. But that's your basic battery. Any questions? Not really a whole lot different than the solution batteries or the solution cells that we were looking at. All of the stuff is exactly the same. The reason that they have this paper here is that instead of having a salt bridge, it's a porous barrier, so it will allow positive ions to move one way and negative ions to move the other, so that the ions can move through the paper while keeping the zinc and the paste physically separated. So it's just a porous barrier that allows that. Any questions? All right, the last part of this that I want to look at, and the assignment to this, by the way, is practice problems numbers 40 to 43, and then at the end of the section, questions numbers 1 through 7, 2.4 questions. Well, I said there were two types of electrochemical cells. The second type is kind of the exact opposite of what we just saw, and these are electrolytic cells. Electrolytic cells convert electrical energy into stored chemical energy. So they're pretty much the exact opposite of a voltaic cell. In a voltaic cell, we make use of a spontaneous reaction to release electrical energy and use that. In an electrolytic cell, we put electricity in to force the non-spontaneous reaction to occur. Remember, non-spontaneous simply meant that the reaction won't occur on its own without the addition of energy. But if we put enough energy in, we can force it to happen. And that's what we do. We put electricity in, it forces it to happen. Well, earlier on we said that gold and silver were very, very stable as atoms, and they tend not to react or corrode like a lot of other metals. But it's pretty much impractical to make a car or a bridge or a tower or something like that out of gold so that it doesn't rust. All right? I mean, think about it. If we were to make the calf rope bridge, all the undercarriage of that out of solid gold so it didn't rust, first of all, it'd be so soft you wouldn't be able to run a car over it. It'd bend. All right? It's gold soft. Second of all, it wouldn't be there very long because people would be going up, chipping off chunks of gold, and pretty soon you wouldn't have a bridge. They'd tear it down. So it's not practical. Okay? Small scale, you got gold-plated jewelry or silver-plated jewelry and stuff like that, and it stays nice. Sure, okay, that's practical. But large scale, it's not practical. So instead, what do? Well, a good alternative is to coat the iron with a thin coat of a more resistant metal like gold. So we gold plate. Don't make it out of solid gold, gold plate. That's done for things like jewelry, obviously, but also stuff like cutlery. So, you know, grandma's good silver, right, that's what they do. They make it out of steel, and then they coat it in silver. Or you can get gold-plated stuff. So you can get grandma's good gold place settings. And there's differing amounts. So, you know, when I started to make up this note, I happened to be at the mall. I went to the Bay. I went to their section that, you know, where they sell all the plates and all that stuff. And I looked it up. And they sell gold place settings and they sell silver place settings there. But the gold place settings, there's a wide range of costs. You know, it can go anywhere from $200 for 4 sets, all the way up to close to, you know, $600 for 4 sets. Like, you know, 4 spoons, knives, forks, that type of thing, right? A place setting for 4. What the difference is the thickness of gold, right? If they got a thicker plating of gold or a thinner plating of gold. So there's that. Basically, the process is the same as with any kind of metal. So whatever you might be plating, whether it's gold, chrome on car parts, you're familiar with that, eh? You know, I mean, you can sell a car that's got painted or plastic bumpers or chrome bumpers and stuff like that, right? You can get it all. You can get the chrome package for more cost, right? And you know, it's basically the same process, and that's called electroplating. And essentially, what we do is whatever we want to plate. So what the object we want to cover over, we connect that as the cathode. That becomes the cathode. And the metal that we want to deposit, we use a solid, pure sample of that, and that we use as the anode. And essentially, all the electrolytic cell does is it moves atoms of that metal that we want to use to cover. It just moves it from the anode across and plates it onto the cathode. So it covers the cathode with that metal. So for example, if I wanted to gold plate a spoon, I'd make the spoon the cathode, I'd make a solid piece of gold the anode, and we are then going to put electricity in, and we're going to force the gold to lose electrons and form into a gold ion, which will then move across the solution. And when it gets to the other side where the spoon is, once it touches the spoon, it'll gain electrons and form solid gold that sticks to the spoon. Basically, that's the gist of it. Okay? So we apply an external power source, and the power source has to be DC. Anybody know what that means, DC power? What's that mean? DC and AC. Yeah, what's DC? What's AC? Anybody know? AC, alternating current. DC is direct current. It must be DC. What comes out of the wall socket is AC, alternating current. Alternating means that the electron flow, just kind of like the term says, the electron flow is continually shifting back and forth. So it's changing directions. And in Canada, I believe our frequency is 60 hertz. So 60 times a second, the electron flow changes direction. In DC power, the electrons always flow in only one direction. They don't change direction. This has to be DC power. So when they do it, they have these big converters that convert AC, which is what everything runs on, into DC, direct current, for doing this industrially. Wherever the solution contacts the object, the metal ions gain electrons, become solid, they coat the object. Your standard cell looks like this. You have DC, and by the way, a battery is DC, direct current, because there's no fluctuation in direction. Eh? So, but we can also have converters or inverters that will convert AC to DC for these purposes as well. Your object to be plated is your cathode, and this is real key. So we're going to be looking for this. It must be connected to the negative terminal on your power source. The cathode is always connected to the negative terminal on your power source, and your anode is always connected to the positive terminal. So notice, in this case, I'm silver plating an object, so the silver metal is connected to the positive terminal on my DC power source, and the object that's being plated is connected to the negative terminal on the power source. And realistically, as far as a power source is concerned, you can draw a box, says DC power, label it, put a positive on one side and negative sign on the other, and as long as you've got everything connected to the right sign, that's good enough. That's all I need as a power source. Doesn't have to be stylized battery, or if you've taken physics, they've got the vertical line. A long line means negative, or long line means positive, and short line means negative. You don't have to worry about any of those conventions. Just draw a box, label it as DC power, positive on one side, negative on the other. As long as you've connected your anode to the positive and your cathode to the negative side of that box, you're good. Okay? So essentially, here's what happens. Because this silver is connected to the positive, this battery will draw electrons out of the silver. Now, my power source would do that too. And there are minimum amounts of voltage that you require. So this is a little bit of a misnomer in that, you can just put a battery in there and it's going to work. You really want to have a power source with a variable voltage, because different cells require different amounts of voltage to run. Okay? But for practical, for demonstration purposes, this works pretty well. And so what we're looking at here is the positive side of things pulls electrons. It provides the force to pull electrons out of that silver and convert them into silver ions, which then go into solution, and at the other side, it pushes electrons down the conductor and into the object that's going to be plated. Well, because we've got electrons going down into this object, the object takes on a negative charge, and the positive silver ions are attracted to that, and they move across. And when they make contact with this object, they gain the electrons that are being pushed in from the power source, form solid silver, and it covers over your object. That's electroplating. Now, are there any questions with that? That make sense? So that's all I've outlined here. As the electrons flow out of the power source and into the solution, other electrons flow out of the electrode and back into the power source. And that way, we still have oxidation occurring at the anode. The anode is still losing electrons, forming ions. And we still have reduction occurring at the cathode, which is the object that's being plated, because you got ions in solution gaining electrons to form solid. Okay, so that's all the same. And as I said, in an electrolytic cell, the anode is connected to the positive, and the cathode is, the anode is connected to the positive, and the cathode is connected to your negative terminal. And so that's how we designate it. So the charge, you know how you have the positive electrode and the negative electrode in the voltaic? You have a positive electrode and a negative electrode here, but they're kind of opposite. The cathode now is my negative electrode because it's connected to the negative terminal. And the anode in these electrolytic cells is the positive electrode because it's connected to the positive terminal. That's how we designate it. They switch. There's a little bit of a switch there, yeah. Okay? So as I said, in this way, we can also plate a thin layer of a metal that corrodes more easily than what we want to. So, if we're trying to make something decorative and that, then, we want something that doesn't corrode and stays shiny. That's why we use silver and gold. But if we want to prevent corrosion, we can galvanize. We can coat in zinc. Now, zinc ions will not react spontaneously with iron. Iron's too high on the chart. So this is the only way to get the zinc ions to gain electrons. So what we would do is, again, we would use a solid bar of zinc, and we would connect an iron pipe as an electrode to the negative terminal on our power source, crank up the power, and we would have that all sitting inside a solution that contains zinc ions, say zinc nitrate. Where the solution contacts the pipe, the zinc ions gain electrons, form solid zinc that's on the pipe. When we put the pipe out to make a fence or something like that, the zinc corrodes, but it forms an zinc oxide barrier that prevents any further corrosion. And even if the zinc oxide barrier is wiped away, because the zinc solid is a better reducing agent, it reacts better than iron, it will react instead of iron. It's called sacrificial anode. And so it acts as the anode, the zinc reacts, and the iron is protected, so your steel pipe doesn't rust. Okay? So once that happens, it acts as a protective barrier, and with the environment locked out, we don't get any corrosion. So we can prevent corrosion that way. That's what we do with chromium as well. That's why we chrome plate, to prevent corrosion.
And then silver tarnishes.
Silver does tarnish, but again, that tarnish doesn't wipe off. It's like with iron, we've all seen it. When it rusts, it's crumbling, it flakes off, and then it exposes more iron. But with all these other metals, when they corrode, they form an oxide layer that sticks. It doesn't flake off. And so as soon as that oxide layer is there, it locks out the environment, doesn't allow any more corrosion to occur. So silver's the same thing. It'll tarnish, but that silver tarnish now acts as a barrier between the underlying silver and the environment. You don't get any more reaction. It's almost like plasticizing it, right? So a little bit of a summary in terms of comparison of the two. Voltaic cell, electrolytic cell, both of them, the electrons flow anode to cathode through the wire, the external circuit. The design is a little bit different. Voltaic cell has two compartments, two separate containers, and it's a spontaneous reaction. An electrolytic cell has only one container, and it's a non-spontaneous reaction. So in the electrolytic, we only have one electrolyte, whereas in the voltaic, we have two electrolytes. And the electrolytes usually are matching the metallic ion in the electrolyte to what the electrode is made out of. Okay? Again, we had that change in the voltaic cell. The anode charge, or the anode is considered the negative electrode or the negative terminal, whereas in an electrolytic cell, the anode is considered the positive electrode or the positive terminal. It's the negative terminal in the voltaic because it's the source of electrons. It's the positive terminal in the electrolytic because it's connected to the positive terminal on the power source. In the cathode, in the voltaic, is considered the positive electrode because it's the destination for electrons, whereas in the electrolytic cell, the cathode is considered the negative electrode because it's connected to the negative terminal. And as far as ion flow is concerned, it's the same in both. Positive ions, cations, will move in solution towards the cathode, and negative anions will move in solution towards the anode. So that's not going to change whether you're talking voltaic or electrolytic. We okay there? So, just to sort of finish up, what do we use these for? Well, remember we started this unit, or this chapter, talking about refining copper in section 2. And at the point we left it at, we had this blister copper that had formed in this molten vat, but it was only about 97% pure. And in order to use it for wiring, it's got to be 99.99%. So this is the last stage. We take that blister copper and we make that the anode. Okay? And we take a pure piece of copper and we make that the cathode. And we put them in a solution that contains copper ions. And we turn on the power. And what happens is it pulls electrons out of the solid blister copper, because that's the anode, and it oxidizes it down to copper ions that go into solution. And those copper ions move across the solution, and when they get as far as the cathode, they regain those electrons and form solid copper on the cathode. But in the process, any impurities, that little 3% that was impurities, it falls to the bottom of the purifying, the electrolytic cell. And so those impurities end up forming sludge on the bottom of the cell. And when we're all done, and the blister copper's all gone, what you have at the cathode is a pure copper cathode that's 99.99% pure, good enough to be used for wiring. So that's the final stage in that copper purifying. Now we do this with a lot of different metals. Use the example of the copper, but they do it with a lot of different metals. Electrolysis is another one. We use this method to break down water to produce oxygen and hydrogen. We use hydrogen for different fuels to burn in industry, and we use oxygen for a lot of different things. Again, oxyacetylene torches, medical grade oxygen for oxygen tanks to breathe for people who need oxygen, and so that's another way we can use this. Electrolysis is simply breaking down. Usually we refer to electrolysis when we're breaking something down into its constituent elements. So it's a breaking down of something. Producing nonmetals other than oxygen and hydrogen. So for example, if we want to produce chlorine, we would use an electrolytic cell and we would electrolyze brine, sodium chloride, and that'll produce chlorine gas. And we use chlorine for a bunch of different things. It's a starting point for bleach, some other things, other industrial processes. So we need chlorine. Typically when we're doing nonmetals though, we can't make an electrode out of those nonmetals. They're not solid. Most of them are gas, quite a few of them are gases. So we would use, again, as I mentioned here, a carbon or a platinum electrode that conducts, but is pretty much, from a reactivity perspective, inert, so it doesn't react. And so it will conduct electricity, it will conduct the electrons, but doesn't react on its own. But the rest of the process is identical to metal refining. And then finally, rechargeable batteries. Okay, in a rechargeable battery, you have both a voltaic and an electrolytic cell all in one single unit. As you decharge the battery, it's acting as a voltaic cell. It's allowing a spontaneous reaction to occur. When you plug it in, so your cell phone, you plug it in, you recharge it, all we're doing is we're taking the anode in the voltaic cell and making that the cathode, and we're taking the cathode from the voltaic cell and making that the anode. So it's connected such that they're connected to the positive and negative terminal appropriately. So the cathode is connected to the negative terminal on the power source, and the anode is connected to the positive terminal. And when we turn on the battery charger, we plug it in, it just reverses everything. So it pulls all the electrons that were gained at the cathode out and pumps it back into the anode so that the anode can regain the electrons, and it restores it to its pre-decharged form. And then you take it out of the charger, you unplug it, and you run your phone again. So we're simply just reversing the process. When you plug it in, that little charger that you plug in, that's a converter. And it converts AC power coming out of the wall to DC power to recharge your battery.
Doesn't like a base station use DC power too?
I don't know. It might have something like that inside, but I don't think so. I think that's all AC.
Well, because like when you plug in the 360, it's not that big block.
Yeah, that's more of I think those are more of a capacitor or transformer than, so it might need more voltage than is coming out of the wall. And so if you take Science 30, you'll learn about this, but it steps up the voltage. So basically it takes 120, I think it's 120 comes out of the wall, and it can take that and step it up to maybe 300 or 400 volts if that's what it needs to run on or whatever. I think that might be a transformer, because I don't believe that it runs on DC. I'm pretty sure it's AC, all of that stuff. Okay? Any questions with any of that? All right, again, practice problems here are problems numbers 44 to 46, and then questions 1 through 7. Okay? So, at this point, if you are inclined to look at this at home, or if you are looking at this at home, you need to go through and you need to do those practice problems from section 4 and section 5, in chapter 2, okay? And that's it for this section.